Now let us talk about frequency multiplication. Or frequency multiplier, anything is fine. Now, I have already mentioned in my previous classes the necessity for frequency multiplication. The basic necessity is to obtain required frequency deviation or phase deviation. So this is the reason why we go for frequency multiplication. So let's have a look at the block diagram associated with frequency multiplier. So it basically contains a transistor which plays the role of an active element, and in between the base and the emitter of the transistor, the input signal is given, and in between the emitter and the collector, in between the collector and the emitter, a band pass filter is connected, a LC band pass filter, and across this LC band pass filter the output is taken. And let me also just show the biasing involved. We'll have a DC voltage source connected in between the collector and the emitter. So this is a frequency multiplier circuit that we are going to deal with. Now let's have a look at the operation involved. Let me just specify the exact input that we are going to apply. Okay. Input is a periodic signal of fundamental frequency f. Now the output is a sinusoid with fundamental frequency n times f, where n is greater than or equal to 1, and it is an integer. As I mentioned already, this is a band pass filter tuned to NF. So this is the story, or this is the initial setup of the circuit that we are going to deal with. Now let us have a look at the actual operation involved. Now one thing which everyone needs to be careful about is the input signal is supposed to be a periodic signal. There is no hard rule that it must be a sinusoid. It can be any periodic signal with fundamental frequency f. Now, some very important points that need to be kept in mind is the transistor is biased in such a way that it is in non-linear mode of operation. So this is how the transistor is supposed to be biased, so that the circuit is going to work as per our requirement. Now the transistor is driven into active region and possibly into saturation. Okay. By the input signal in the vicinity of its peak excursion. So this is what the situation is. The collector current flows when the transistor is on. So this is what we have. And as we go along, we see that though the collector current which is periodic has a fundamental frequency of f so just like the input, but is rich in high frequency harmonics. So this is the nature of the collector current. Now the band pass filter that we are dealing with resonance circuit offers very low impedance impedance to all frequencies except the nth harmonic. Of the collector current. Why? Because it is tuned to NF. Because of this, the voltage developed across its terminals is not of appreciable value for all harmonics except the nth harmonic. So because of this reason, because of this, the out of BPF is a periodic signal with fundamental frequency NF. Now moving on, so it has already been mentioned that the output is a signal of fundamental frequency NF, and it is basically periodic, and it is a single tone sinusoid. Okay, so that is the final thing. Now to finish it up, the value of n can take any value, as per the requirement but higher the value of n, weaker the corresponding harmonic is going to be. Okay, let me just add, weaker the corresponding harmonic is going to be of the collector current. So this is what we have from this circuit. We can get a frequency multiplication in the range of 2 to 5, or in other words, from the circuit let me just correct it. It's not current, it's the circuit. From this circuit, the achievable value of n is from 2 to 5. So this is what we have, and I'm sure you must be wondering, what are we supposed to do if we need a multiplication or a value of n greater than 5? In that case, you're supposed to use frequency multiplier in cascade. So multiple frequency multipliers can give you a higher level of frequency deviation or modulation index or phase deviation. And I'm sure you must be thinking how the output of the band pass filter is a periodic signal. Let me just take a simple example to explain you that. Let the input be a single tone sinusoid. Now what do we have? The figure, you have a look. Let this be something like this. A single tone sinusoid. Input to frequency multiplier. This is T. Now the collector current, let us have a look at the collector current. Now we already know that the collector current flows in the vicinity of the maximum excursion of the input signal, or in other words, you can assume it's something like this. So this is the maximum positive excursion we have. This value gives you the maximum positive excursion. So in its neighborhood, okay, the transistor is going to have collector current. So let us assume, or let us consider this particular interval as the vicinity with respect to the maximum positive excursion. So for this duration, whatever you see, we are going to have the collector current. So if you just extend this, then we are going to have pulses. Let me just show you over here. So this is what we are going to get. Have a look. This is how the collector current is going to be. Obviously these are periodic. That's the reason why the collector current is periodic, and if once we use Fourier series to represent this particular signal, the band pass filter is going to give the best possible output in terms of energy to the nth component of it. So this is how frequency multiplication is achieved, and the end result, as we all know, high frequency deviation or high phase deviation.